Okay, morning everyone. Okay, so now we're gonna start our lecture. Okay. All right, so we're gonna continue from last time where we were talking about these two problems called max flow and min cut. Okay. So just to sort of remind you, so for the max flow problem, we're basically we're gonna take a graph and then you have these two special nodes in the graph, right? So the source node and the sink node. Okay, so in this graph it's S, the source, and the sink is T, right? And our goal is, so we're gonna think of this graph as kind of like a network of pipes, of water pipes, let's say, right? And our goal is to send a lot of water, or as much water as possible, from S to T, right? And because these are pipes, we have these constraints on the pipes, which are that each pipe has a capacity, right? So these numbers that we have over here are like the maximum water you can send through this pipe, right? And also there's this other constraint, which is the conservation constraint, which just says that for each of these junctions, where you have several pipes that meet at this junction, right? So all the water that you have coming into the junction has to go out, right? So if you sum up all of the edges going into a node, if you sum up the flows on all the edges going into a node, and then you subtract all the flows on the edges leaving that node, that has to be equal to 0 for every single node, except for S and T, right? Because S is going to produce a lot of flow, and then T is going to absorb that flow, but every other node has to conserve the flow. Okay, so that was the max cut the max flow problem. And then the min cut problem is this other problem where now what we're trying to do is, let's see, I guess I can, what was it? Yeah, okay. So the cut problem is that now we're gonna again take a graph with these two special nodes S and T, and you're gonna partition the graph into two parts. Okay, so you have this gray part, which is A, and everything else is in B. Right? And then now we're going to look at the capacity. Oh, and the restriction is that S, right, this source node has to be part of A, and T has to be part of B. Okay, so that's the restriction on the partition. And then after that, we're going to look at the capacity of the cut, which is that we're going to look at all of the edges which go from A to B, and we're going to sum up their capacities. Okay, so for example, in this case, we have 5 edges that cross between A and B, but only 4 of them are going to go from A to B, right? One of them goes from B to A, and we ignore that edge. So if you sum up all of these capacities that go from A to B, that is the capacity of this cut. Okay, and okay, so then once we have this idea about cuts, then we have this interesting relationship between flows and cuts, okay? Which is that if you take any flow, okay, so if you take a graph and then you take any flow on that graph, okay, and then you take, so any flow and then any cut, okay, then it turns out that this flow is going to be less than or equal to the capacity of the cut. Okay, so this is called weak duality because it relates flows and cuts. Okay, and the reason for this is actually pretty straightforward. Yeah, so it's that suppose you make any cut. Okay, for example, this is a gray cut over here. This is our A, right? Well then, if you have a flow, then because S is by definition going to be part of A, okay, then all of the flow originally comes out of S, right? And so if you and because the flow has to go into T, and then T is in B, right? It's in the other side of the cut. Okay, then all the flow has to cross from A to B at some point. Okay, and when it crosses from A to B, it has to go through one of these edges in the cut, right? It has to go through either this edge or that edge or that edge. Oh, or sorry, not this edge, wrong one. Or this edge. Okay. Yeah, so all the flow has to go through those edges, right? I mean, it's not going to go through any of these back edges from B back to A, right? Because we're trying to send flow from A to B, so we're not going to use these back edges from B to A. Okay? So it has to go through these A to B edges, and then if you sum up their capacity, which in this case is 28, right? Then that means that there's no way to send more than 28 units of flow from A to B or from S to T. right? Because all 28 units have to go through these pipes, right? And these pipes can only hold 28 units of flow. So so that means that this flow cannot be more than the capacity of the cut. Okay, and this holds for any cut, right? Like if you get a different cut, right? Or sorry, let me just use the same picture. Okay, so if you had a different cut, like if you had this was your A, right? Then your capacity would be what? It would be like here 9 plus 15 plus 8 plus what do we have here? 30. Okay, so whatever that number is, that's probably larger than 28. But that also says that, this sum here is a upper bound on your flow. Okay, yeah, so that is the weak duality property. Okay, so now what we want to talk about today is a stronger duality. Okay, so in fact, we're gonna look at these two theorems, these two theorems up here. Okay, so remember that our way for solving a max flow was that we talked about this Ford-Fulkerson algorithm. Okay, which is going to, sorry, let me close my window for 1 second. Okay, I'll be right back. Okay, yeah, it's too noisy outside. All right, so we talked about this Ford-Fulkerson algorithm, which is, we're gonna take this residual graph, right? So remember how we built the residual graph, okay? So we take this residual graph, and then you look for an augmenting flow in the residual graph, right? And if you can find one, then you can increase your flow along that augmenting flow. Right? And then after that, you're going to build a new residual graph based on the new flow. And again, you try to augment the flow. And you just keep doing that until you get a graph where you cannot find an augmenting flow within that residual graph. Okay, and then you have to stop. Right. So now what we're trying to prove is that when you terminate this algorithm, you're actually going to get a max flow. Okay. And furthermore, what's interesting is that this max flow is going to be equal to the value of a min cut. Okay, yeah. So previously the duality property said that where is it? Yeah, the max flow is no more than the min cut, right? Because here you can take any flow, including the max flow, and then here you can take the min cut. And so weak duality says that max flow is less than or equal to min cut. Okay, but strong duality, which is this max flow min cut theorem, says that max flow is equal to min cut. Okay. All right, so now the way we're going to prove this is we're going to take these three statements. Okay, so suppose you have any kind of flow, okay, any flow F. So now we have three statements, and we're going to show all three statements are equivalent to each other. Okay, so the statements are that suppose, so we start with the flow F, and suppose you can find a cut AB such that the amount of flow is equal to the capacity of that cut. Okay? All right, so that's the first statement. Second statement is that F is a maximum flow. Okay, and third statement is that if you look at F, then you cannot find any augmenting path in the residual graph for F. Okay, so we're going to show that all three statements are equivalent to each other. And if we can show these statements are equivalent, then we can prove both the max cut. We can prove both theorems up here. Okay, because yeah, for example, if we show that 2 and 3 are equivalent, right, then that is exactly the augmenting path theorem, right, which says that you have a max flow if and only if you do not have any more augmenting paths. Okay, that's just saying that statements 2 and 3 are equivalent. Okay, and then for the second theorem, right, for this max flow min cut theorem, so if you so if we show that statements 1 and 2 are equivalent, okay, then what we're saying is that if you have a maximum flow, right, then there is a cut with exactly this capacity. Okay, and this cut also has to be a minimum cut. Okay, so if there is a cut with capacity equal to the flow, that cut has to be the minimum cut. Okay, because if you have another cut which has even lower capacity, okay, so suppose this AB here is not the minimum cut, so there's some other cut with even smaller capacity. Okay, well then that other cut would have smaller capacity than this flow, right? Because we're saying our max flow is equal to this AB cut's capacity. So if you have another smaller capacity cut, that cut has smaller capacity than this flow. Okay, but that's impossible by the by the weak duality property, right? Which says that any flow is no more than any cut. Okay, so therefore, if you ever can find a cut which is equal to the flow, then that cut is minimum, right? And also that flow is maximum. Okay, so 1 and 2, statements 1 and 2 imply the max max flow min cut theorem. Okay, so now so now let's prove all three properties are equivalent to each other. Okay, so first of all, let's say that let's show that 1 implies 2. Okay, so 1 implies 2 because by weak duality we have that any flow is less than the capacity of any cut, right? And so therefore, if you have a flow which is actually equal to this capacity, right, then this is as large as you can possibly make that flow. Okay, you cannot make the flow larger because in that case you would have the flow would be larger than the capacity of some cut, which violates weak duality. Okay, yeah, so therefore 1 implies 2. Okay, also we have that 2 implies 3 because so we're going to show the contrapositive, okay, meaning that if you don't have 2, okay, so if you don't have 3, okay, so no 3 implies no 2, okay, that's the contrapositive. So so if 3 is false, then that means that there is an augmenting path relative to this current flow. Okay, well then we can increase our current flow, right? Because we can just add more flow along this augmenting path and we get a bigger flow. And that means that the current flow F is not a max flow. Okay, so if there is a augmenting path, then F is not a max flow. And so therefore 2 implies 3. Okay, if it's a max flow, there cannot be any augmenting path. Okay, and the final part is to show 3 implies 1, which is that if there is no augmenting path, then there has to be a cut with capacity equal to that flow. Okay, all right, so then so then suppose you have a flow with no augmenting paths. Okay, so F is such a flow. So then now we're going to build up this special cut. Okay, we're going to actually construct a cut whose capacity equals the flow. Okay, so the way we're going to construct this this cut is that we're going to define a set A to be we're going to first of all look at the residual graph for F. Okay, right? So once you have F, you build a residual graph, and now A is going to be the set of vertices which are reachable from S in the residual graph. Okay, like not in the original graph, right? But in the residual graph. Okay, A is defined as the set of vertices reachable from the source in the residual graph for this flow F. Okay. All right, now by definition, you have that S is reachable, right? So therefore S is in A, okay? And also because F is a flow with no augmenting paths, okay, then T cannot be in A, okay? Because if T is in A, right, then T is reachable from S by definition, right? A is a set of vertices you can reach in the residual graph. So if T is reachable from S, so if T is in A, then it's reachable from S. But if T is reachable from S, then that means that you have an augmenting path from S to T, right? Because the residual graph are all of these edges where you can add more flow onto those edges. Okay, so if you can reach T from S, then you can add more flow on some path from S to T. And so that would mean that there is an augmenting path. Okay, but because we're assuming that there is no augmenting path, then this means that T is not part of A. Okay, so therefore, the picture that we have, okay, is going to look like this. Okay, so we're going to divide the graph into 2 parts, A, and then everything else is going to be called B. Okay, and we know that S is part of A, and we know that T is going to be part of B. Okay. All right. Now, by the way, these edges in here that I'm showing in this picture, this is the original graph. Okay. This is not the residual graph. This is the original graph. Okay. Like it says over here. Okay. So let me clean this up a little bit. All right, so now we're going to look at some properties about this graph. Okay, so there are two types of edges in this graph. They're the ones that go from A to B, right? So for example, this edge goes from A to B. Okay, and then there are these edges that go from B to A. Okay, now let's look at the edges from A to B first. Now, the claim is that these edges, so there's some sort of flow on these edges. Okay, let's call that f of e. So this edge here is e, and there's some flow on this edge. Okay, now the claim is that this flow has to be equal to the capacity of the edge. Okay, that's what we claim. Okay. And the reason is, suppose this flow is actually strictly less than the capacity. Okay, then you can add more flow onto this edge. Right? And so that means that in the residual graph, okay, this edge would exist from, from A to B, right? Because in the residual graph, as long as you can add more flow onto an edge, you're going to keep that edge in the residual graph. Okay, so if the flow is less than the capacity, then this edge exists in the residual graph, but then that would mean that this node over here is still reachable from S. Right, so that node here should be actually part of A, because A is everything you can reach from S. Okay, right, but this node here actually is not reachable from S, and so that means that in the residual graph there is no edge from from this A node to the B node. Okay, and if there is no edge from this A node to the B node, then that means that the capacity has to be the flow has to be equal to the capacity. Right? Because once you have the flow is equal to the capacity, then you take out that edge from the residual graph. Okay, so we have this property. Okay, so the next property that we have is that now we're going to look at these edges from B going back to A. Okay, and the claim is that all of these edges have to have zero flow on them. Okay, and the reason is that suppose this edge actually had positive flow on it. Okay. Then what we did was that if you have an edge with positive flow, then in the residual graph, you're going to convert that edge into two edges, right? One in each direction. Okay, so let's say that this edge currently has a flow of 1 on it, okay? Out of a capacity of 10, let's say, okay? Then when you build the residual graph, what you're going to do is you're going to set the residual capacity here to be 10 minus 1, which is 9. And you're going to set a capacity of 1 for this new edge from A to B. Right? That's just how you build the residual graph. Okay. As long as you have flow on an edge, then you convert that edge into two bidirectional edges, right? And then you set the capacities this way. Okay. So if there is positive flow, then there is an edge from this node over here, right? From the A node to this B node. Okay. But then again, that would mean that this B node here should actually be part of A, right? Because this B node is now reachable via this additional edge in the residual graph. Okay, and so because this node is actually not reachable, right? Then this means that there is no additional backwards edge, right? And the only case where you don't have a backwards edge is when your flow is 0 on that edge. Okay. All right. So therefore, we've shown these two properties. Okay, which is that on all of these A to B edges, the flow is equal to the capacity, and on all of the B to A edges, the flow is 0. Okay. All right. So now we can go back to this expression over here. Okay. So remember that this expression, this was like one of these properties that we proved about the. So this is the size of the flow. And we said that the size of the flow is always equal to, you can take any cut you want, right? And then you look at all of the flow going out of that cut minus all the flow going into that cut. Right? So this always holds for any cut A. Okay? And so in particular for our for this A that we have over here, right? For this A that we constructed, right? We have this relationship. Okay. Right, but now look at this. So we have that for all of the edges going out of A, right? So these are these types of edges, okay? these types of edges have flow which is equal to the capacity of the edge. Okay, right? So therefore you have this relationship because these two things are equal to each other. And now for this other part where these are edges going into A, you have that their flow is 0. Okay, so this thing just is all 0. Okay, so therefore you have that, yeah, so therefore you have that the flow is actually equal to this expression over here. But that expression is by definition the capacity of A. Okay? All right, so what we did was that if you have this augmenting flow, so just to summarize, so if you have a flow with no augmenting paths, okay, then we constructed the set of reachable nodes in the residual graph, right? And we showed that for this set of reachable nodes, right, for this A, okay, you have that the flow is exactly equal to the capacity of that edge, of that cut. Okay. All right. So now we've shown that all of these statements imply each other. Yeah. And so they're all equivalent. And so as we said, this proves both the augmenting path theorem and the max flow min cut theorem. Okay. And so in particular, it shows that Ford-Fulkerson gives you a max flow, okay? Because Ford-Fulkerson keeps on running until you cannot find augmenting paths anymore, okay? Okay, any questions about this? Any questions? Okay, so, all right, okay, so now let's sort of, so the next thing we're gonna do is look at the time complexity of Ford-Fulkerson. Okay, so we've just shown that this algorithm is correct, but we didn't talk about how much time it takes to run. Okay, right. So so to analyze the complexity, let's assume that all of the capacities here are between 1 to some number C. Okay, and right. Okay, so first of all, we have this invariant. Okay, which is like a property which is always true as you run the algorithm. Okay, and the invariant is that suppose the capacities are all integers. Okay, then as you run the Ford-Fulkerson algorithm, we're going to look for these augmenting paths, right? And so like initially all the capacities are integers, so the first augmenting path you find, right? The amount of flow you can send on that path is an integer, right? Because all the values in the graph are integers. So therefore, the amount of flow on the first augmenting path is an integer. Okay, right. And then once you find that first augmenting path, you're going to reduce the capacities on some edges, right? And then you add these back edges and so on. Okay, but after you do that, everything, all the capacities are still integers, right? Because they start out being integers, and then you subtract or add another integer, so they remain integers. Okay. And then in that new graph, again, you find an augmenting path, okay? And because all the values in that graph are integers, that new augmenting path also has, is an integer, okay? The amount of flow on that new augmenting path is an integer, okay? Yeah, so you can see that as you run the algorithm, everything stays integral, okay? The residual graphs always have integer capacities, and so the augmenting paths you find are always integer valued. And so that means that the final flow that you produce, which is like summing up all of the augmenting paths, right? That is going to be an integer. Okay, right? So therefore we have this integrality theorem, which says that if all the capacities are integers, okay, then there's a max flow where the flow value is also an integer. Okay, there exists a max flow where the flow value is integral. Okay. Now, there could be other max flows where the flow is not integral, okay? But there is at least one max flow where the flow value is integral, and this is just because as you run the Ford-Fulkerson algorithm, you always maintain an integral flow. Okay, right. So this integrality theorem, it's actually quite important because we're going to use this in multiple places to prove other things. Okay. Right, so one direct consequence of this integrality theorem is that we can now analyze how much time it takes for Ford-Fulkerson to terminate. Okay, because we can say that the algorithm, the Ford-Fulkerson algorithm, terminates in at most n times c iterations. Okay, and okay, right. So it terminates in at most this number of iterations, where each iteration is you find an augmenting path. Okay, and the reason this is true is because so each augmentation is going to increase your flow value by at least 1. Okay, and then your flow value can be at most n times c, right? Because you have the source node, right? And then each of these capacities is at most c, and so this is like s over here. Okay, so your flow, so you have like at most you have like n nodes over here, right? So therefore your max flow can be at most n times c. Okay, and because every iteration you increase your flow by 1, then this means that after nc iterations, the algorithm has to terminate. Okay, and so this tells you that the running time of the Ford-Fulkerson algorithm is m times n times c at most. Okay, because each of these iterations might take you order m time to run, because you need to go through this entire graph and find an augmenting path, which involves something like BFS or DFS, right? And that's going to take you order m time per iteration, and you have n times c iterations. Okay, so therefore the running time of Ford-Fulkerson is this value. Okay. All right, now the problem with, okay, so we have some sort of upper bound on the running time. The problem is that this upper bound can be quite large if c is large. Okay, so for example, suppose that c is some sort of like, let's say it's a 32-bit number. Okay, so it can go all the way up to like 4 billion. Okay, so that means that the running time of Ford-Fulkerson is m times n times like 4 billion. Okay, if c is like a 64-bit number, right, then, I mean, I don't even know what 2 to the 64th is, right? It's some humongous number, right? In that case, if you have, a graph where the capacities are 64-bit numbers, then the running time of Ford-Fulkerson would be like, humongous. Okay, so so the basic problem is that Ford-Fulkerson might not be efficient. Okay. All right. So, but you could say that. All right. So this theorem. Sorry. Let me erase this. Oops. Okay. So you could say that this theorem over here, right? This is like an upper bound on the number of iterations, but this is a worst case upper bound. Okay. Maybe for Ford-Fulkerson, you never actually run n times c iterations. Okay. Maybe you always run like order n iterations or something. But it turns out that you can actually run many order nc iterations, or at least order c iterations in Ford-Fulkerson. Okay, so as an example of this, suppose you have a graph like this. Okay, so let's see, is there better? Okay, so this graph, you have basically you have just 5 edges over here. Okay, and these edges along the boundary, right? They have capacity c each. Okay, right, so that's the C. And then you have this one middle edge, which only has a capacity of 1. Okay. All right, so now suppose you run Ford-Fulkerson on this. So first of all, the max flow on this graph is going to be 2 times C, right? Because you can just send C flow this way, and you can send C flow that way. Okay, so that's the max flow. And but if you run Ford-Fulkerson, you could end up always finding these sorts of augmenting paths, right? So this is an augmenting path, but the the bottleneck for the path is just amount 1. So you can only send one amount of flow on this path. Okay, so yeah, so you run one iteration and you increase the flow by 1. Okay, and then you run a second iteration, and let's say that you got unlucky and you found this as your augmenting path. So now your total flow is 2. Okay, right? And then you can just switch back and forth like this, okay? Because in the third iteration, you can again find this thing as your augmenting path, and now you're gonna have like 2 flow over here, right? What is this? Yeah, this is 1, and so now your flow becomes 3. Okay, so as you run the Ford-Fulkerson algorithm, you can just alternate. You can just alternate between these 2 augmenting paths. Okay, and each time you just increase your flow only by 1. Okay, but we know the max flow is going to be 2c, And so this means that on this graph, it's going to take you like 2 times c iterations in order to terminate. Okay, so we see that indeed it is possible for Ford-Fulkerson to run for like many iterations. Okay. All right, so now we want to solve max flow, but we want to find like a better algorithm, a faster algorithm. Okay. And the thing is that so even though we're going to look for a different algorithm, we're still going to use the same approach as Ford-Fulkerson, which is to find these augmenting paths. Okay, because we know, because whatever algorithm you use, okay, we know that this theorem, okay, so it doesn't matter that this was proved by Ford-Fulkerson, okay, this theorem holds for any algorithm, okay, it should be, I guess, this theorem, okay, this holds for any algorithm, which is that if you if you don't have any augmenting paths, then you have a max flow. So basically, any kind of max flow algorithm, you can design it just to find augmenting paths, okay? And then eventually, once the algorithm cannot find augmenting paths anymore, then you know you have a max flow. So the only difference is, how are you going to find these augmenting paths? Okay, there might be many different ways to find augmenting paths. Okay, so our goal here is to somehow efficiently find these augmenting paths. Okay, we want to find the paths quickly, right? And we don't want to do it for many iterations, right? Because previously, for this Ford-Fulkerson, you had to do this for like order c iterations. That was a big problem. Okay? So therefore, you want to find augmenting paths where you can find each path very quickly, and you don't need to go for many iterations overall. Okay, all right. So therefore, all right. So there are many algorithms, in fact, for max flow for doing these two things. Okay, for finding augmenting paths quickly and making sure you don't have to go too many iterations. There are many such algorithms. Okay, there's like dozen, or maybe at least like a dozen algorithms. Okay, and in fact, in recent years, there's been I think in just like the last 5 years, there's been like sort of a new approach to how to find these max flows. Okay, so there's been renewed interest in this problem of max flow, even though this problem is very old. It goes all the way back to the 50s, right? So it's like over 70 years old, but there's still interest in this algorithm. Okay, all right. So yeah, so I'm today just going to talk about one particular algorithm, which is called capacity scaling. Okay. All right, so the basic idea for capacity scaling was that, well, let's go back to this example for this worst case example, okay? So the problem here was that when you find these augmenting paths, right, you only increase your flow by a tiny amount, right? And your max flow is very large, so therefore you have to run many iterations because each iteration is very ineffective, right? It only increases the flow by a tiny amount, okay? So what we want to do basically is to look for flows which are large. Okay, each iteration we want to increase the flow by a big amount, right? And that would mean that in total you don't run many iterations. Okay, yeah. So our goal is to make sure that in each iteration we can increase the flow by a lot. Okay, and so how would you do that? How do you make sure that in each iteration you increase your flow by a lot? Okay, well, suppose you have a graph like this. Okay. Then if we want to make sure our flows are big, we want to not use this middle edge. Okay, because if you use that middle edge, right, then this limits your flow to just size 1. Okay, so you don't want to use these edges which have very small capacity. Okay, in fact, you want to just maybe remove that edge. Okay, so this that's what this GF100 is. Okay, it's only going to keep all of the edges which have capacity at least 100. Okay, we're going to take out all of the smaller edges. Okay, and if you look for a max flow in this graph, right, then the max flow has to be if you look for an augmenting path in this graph, okay, that augmenting path has to have lots of flow on it, right? Because even the minimum capacity in this graph is like 102. So if you find an augmenting path, you have to increase your flow by at least 102. Okay, yeah, so we're going to go from this original graph to this this other graph where you take out these small edges. Okay, right? But the problem is that if you take out the small edge, okay, you might also change your max flow. Like this graph over here might have a smaller max flow than the original graph. because you took out some edges from the original graph, right? So therefore, the idea is that we are going to go from this original graph to this to the special graph with only big edges, right? And then we're going to find a flow in this special graph. Okay? But then after that, we're going to add back in the edges that you took out. Okay, we're going to add in this this other edge later on. Okay, but when you add in the edge, you've already found a. So we're going to initially we're going to start out by finding flows in this GF100 graph. Okay, and those are going to be big flows. And then after that, we're going to add back in the edge that you took out, and then you're going to maybe try to increase your flow a little bit by using this edge. Okay. But we're going to show that you know, even though you added this edge back in here, you won't have to do too many more iterations, okay? Because you've already found a very big flow in this graph, and so so at most you can increase that flow by a little bit after you add in this edge. Okay, all right. So that's the basic idea for this capacity scaling algorithm. Okay. All right, so in particular, what we're going to do is we're going to take all of the, so we're going to start with this graph G, okay? And that's going to have a bunch of capacities in it. And then now we're going to sort of divide these capacities into buckets, which are powers of 2, okay? Yeah, so for example, suppose you have an edge with capacity, let's say 20, okay? So then that's going to go into this bucket between 16 and 32. Okay. If you have an edge with capacity, let's say 10, it's going to go into this bucket. Okay. And if you have a one with capacity 30, it's going to go into this bucket. Okay. Right. And now what we're going to do is initially we only want to have the big edges. Right. You see in this GF100, you only keep the big edges initially. Okay. So therefore, what we're going to do is initially we're going to look at all of these edges in the graph. Right? And suppose you have one over here, which is like 5, and you're only going to keep the final bucket. Okay, so you're only going to keep these 2 edges with big capacities, and you're going to remove all of the other edges. Okay, so we're going to call that this GF delta graph. Okay, where delta here is equal to the largest power of 2, which is less than your maximum capacity. Okay, so for example, your maximum capacity is like 30 over here. So this GF, so we're going to form this GF of 16, right? And this is only going to keep all of the edges which have capacity at least 16. And it's going to remove all of the other edges. Okay, right. And then you're going to go find a max flow in this GF16. Okay, you're going to use Ford-Fulkerson, let's say, to find a max flow in GF16. And then after you find max flow in GF16, then next we're going to add back some of these other buckets that we took out, right? So we took out this bucket, right? So we're still going to take out this 5 edge because it's very small, okay? But we're going to add back in this 10 edge, okay? And so now we're going to have this graph, which is GF8, which is going to have all of the edges with capacity at least 8. Okay, so that'll be 3 edges over here. And then in this bigger graph, we're going to update our flow, right? Because let's say that you found, let's say, flow 1 in here, okay? And then now you're going to find flow 2 by updating flow 1 to include this extra edge, to potentially include that extra edge, okay? All right, and then after you find this F2 over here, then next, you're going to bring in the edges from the next bucket, which is this 5 edge, right? So we're going to bring this guy in. So now we're going to have GF, of 4, right? And then you're going to find this flow F3 in here, which you get by updating F2. Okay, so that's the algorithm. Does that make sense how this works? Right, initially you throw away lots of edges. Why delta is 16? Oh, okay, right. Yeah, so initially delta is going to be like the largest power of 2, which is less than your maximum capacity. Okay, so let's say your maximum capacity is 30, so then delta is going to be 16. Okay, yeah. So again, the idea is that initially you just want to keep the very biggest edges. Okay, and then you find a flow in that graph, And then next, you bring in the next batch of smaller edges, but they're still very big, right? But they're smaller than the biggest edges. Okay, you find a new flow, and then you bring in more edges, which are even smaller, and you keep doing that eventually till you bring in all of the edges. Okay, so after you bring in all of the edges, okay, so we have this correctness theorem, okay, which says that if you run this capacity scaling algorithm, you will get a max flow in the end, okay? Because in the end, we're going to end up with delta equals 1, okay? And when delta equals 1, that means that we're going to use all of the edges, okay? And this algorithm terminates when you cannot find augmenting paths. And so that means that in the original graph, if you cannot find any augmenting paths, then you have a max flow. Okay, any questions about this? Okay, so all right, so now let's look at the running time for this new algorithm, okay? So we have a few lemmas here. So the first lemma is that the outer loop, right? The outer loop is this loop over here, okay? This is gonna run for order log C iterations, okay? And that's just because in each iteration, we're gonna decrease our delta by a factor of 2. Right. So yeah, so in total, you're going to run this number of iterations from like, let's say 32 down to 1. So that's going to be log of C iterations, right? Initially, delta is going to be basically C. Okay, so that's yeah, so that's lemma 1. Okay, lemma 2 is this important lemma, which is saying that suppose so we're going to run multiple phases of this. Right. So let's say in the current phase we're using delta, and then in the next phase we're going to use delta over 2. Okay, right, and then delta over 4, and so on. Okay. Now suppose in this delta phase, right, you found some sort of flow f, okay, which has this amount of flow, right, right. Then then this lemma says that the maximum flow, okay, which is what we're trying to find, right. So sorry, I can't write anymore. What's wrong? What's wrong with my computer? Okay. All right. So sorry, guys. 1 second. My computer is like misbehaving or something. What's this? What's happening here? All right. Why can't I write anymore? Edit. Oh. No, I don't want that. Okay. All right. Okay. Yeah. Sorry. Okay. So lemma 2. Okay. Lemma 2 says that in this current delta phase, you found some sort of flow f. Okay. Now, eventually, you want to find the maximum flow, and the claim is that the maximum flow cannot be much larger than the current flow that you have, which is v of f. Okay. So in fact, the maximum flow can be at most the current flow plus m times delta. Okay. That's the claim. Okay, and the final part over here. So we're going to prove this on the next page. Okay, but let's first look at lemma 3, which is that for each phase, okay, for example this delta phase, right, you have at most 2 times m augmentations. Okay, and the reason for this is because suppose you had a flow f from the previous phase, okay, from the previous scaling phase. Okay, then by this lemma 2, we know that the optimum flow, which is this f star, is going to be at most the previous flow from the previous phase, right, plus m times 2 delta. Okay, it's 2 delta because the previous scaling phase, so if we're currently in a delta phase, then the previous scaling phase was 2 delta. Okay, so therefore by lemma 2, we know that the max flow is going to be at most the previous flow plus m times 2 delta. Okay, and now in our phase, okay, in the current delta phase, each time you find an augmenting path, this has to increase the flow by at least delta. Okay, by at least delta. Okay, and the reason is because in this phase, we only have edges which have capacity at least delta. Right? In the delta phase, you only keep edges which have at least capacity delta. Okay, so because so therefore each augmentation increases the flow by at least delta. And because the max flow is at most the previous flow plus m times 2 delta, then this means that you can do at most 2m augmentations. in the current flow before you find the max flow. Right? Yeah, I mean, maybe you don't find the max flow in the current phase, okay? But in any case, you cannot do more than 2m augmentations, because if you do more than 2m augmentations, your flow would be larger than the max flow. Okay, that's impossible. Okay, so this says that every scaling phase is fast because you only do 2m augmentations. Okay, furthermore, you don't do many phases. Okay, so therefore you can combine everything together and you can say that we do at most m times log c number of augmentations, right? Because you do this log c number of phases, and for each phase you do 2m augmentations at most, right? So therefore in total you do this many augmentations. Okay, and each augmentation again takes you order m time to find by BFS or DFS. Okay, so therefore your total running time is just this thing times m, which is like m squared times log c. Okay, does that make sense? Any questions? Okay, so yeah, so I'm gonna take a short break now. I'm gonna take just a 5-minute break, okay, because we have a lot more to talk about. So just please come back at 11:05, okay, and then when we come back, we're gonna finish proving this. So the final part is to prove lemma 2, okay. So we'll just prove lemma 2 after you guys come back, okay. All right. So does anyone have any questions about anything? Right. You can just say your question also. If it's like very complicated, you don't have to type it out. You can just say it. Let's see. Can you reiterate the proof for lemma 3? Oh, okay, sure. Yeah, yeah. I think the network was like not very stable. So, by the way, I put a recording of the previous lecture on Blackboard, right? So you guys, you saw that, right? Yeah. So hopefully that doesn't have any of these disconnection problems. Okay. So for what is this? All right, so I'm gonna erase this. All right, so for lemma 3, let me erase some stuff. All right. Okay, so yeah, so the idea here is that by this lemma 2, okay, we know that whatever flow you found in the previous phase, which was the 2 delta phase, right? Whatever flow that was, that flow is, the maximum flow is no more than the previous flow plus m times 2 delta. Okay? All right, so therefore, when you start the current delta phase, basically all we need to do is we need to increase our flow by maybe this amount, m times 2 delta. Okay? If we can do that, then we definitely have a max flow. Okay? Right. And then how many augmentations does it take to increase our current flow by m times 2 delta? Okay. Well, because we're only keeping edges of size at least delta, then each time you do an augmentation, you have to increase your flow by at least delta, right? Because even if you look at the minimum capacity edge on the augmenting path, that has capacity at least delta. So we're going to increase our flow by at least delta each augmentation. Okay, and so since you only have to increase your flow by at most m times 2 delta, then this means that you can do at most 2m augmentations. Okay, because if you do more augmentations, your flow would exceed the maximum flow, which of course you cannot do. Okay, guys. So hopefully you're back. Well, I'm gonna continue with this just because I have too many things to talk about and not enough time. So anyways, I just want to finish with this proof of lemma 2 over here. Right. So lemma 2 says that after you run the previous phase, then you basically already found a flow which is very large. Okay. There's just a remaining gap of m times delta compared to the maximum flow. Right, and so the proof is very similar to the proof of the max flow min cut theorem. Okay, so basically what we're going to do is suppose you finish a delta phase. Okay, then we're going to show that there is a cut whose capacity is at most the current flow plus m delta. Okay, and now because you know that any flow is less than this capacity, right? That is a weak duality property. Okay, then that means that the max flow cannot be more than this value over here. Okay, so as long as we can find this cut with this small capacity, then that means that the max flow is not much larger than our current flow f. Right, and the way that we do this is basically the same as for the max flow min cut theorem, which is that again you're going to define the set A to be the set of nodes which are reachable in this residual graph, where you only keep these big edges larger than delta. Okay, so in the previous version of this proof, you just look at all the edges in the residual graph, which are reachable from A. Right, sorry, all the nodes reachable from A. Okay, now here we're going to throw away some edges. Right, so so we're going to look in this reduced graph, reduced residual graph. Okay, you're going to look at all the nodes reachable from A. Right. Now, again, S is reachable from A, obviously, okay? And also T is not reachable from A, because if T is reachable from A, then there's an augmenting path from S to T. And in that case, we cannot terminate this phase. Right? You only terminate the phase when you have no more augmenting paths. Okay? All right, so T is not reachable from A. So therefore, the picture, again, looks like this. Okay, you have this A, which is all the reachable nodes from S in this residual graph, and then B, which contains T. So again, we're going to look at these edges that either go from A to B, right, or from B to A. Okay. Now, from the A to B, for the A to B edges, okay, we claim that the flow here has to be at least the capacity minus delta. Okay, because suppose the flow is less than capacity minus delta, right, then you would actually include this edge in the residual graph, right, because your leftover capacity would be larger than delta. Right? And in this GF delta thing, we include all of the edges which have size at least delta. So therefore, if you have flow is less than capacity minus delta, you would have this additional edge over here, but then that would mean that this node is part of A, okay, which is a contradiction. So that means that all of the flows here on these AB edges have to be at least capacity minus delta. Now, for these BA edges, we claim the flow has to be at most delta. Because if the flow is larger than delta, okay, then we would add this reverse edge with capacity larger than delta. Okay, and then this reverse edge would be part of this GF delta graph because you keep all edges larger than delta. Okay. And so that would mean that, again, you can reach this node from S, right, which is not possible. So that means that all of these BA edges have flow at most delta. Okay. All right. So now we can go back to this. So the definition of the flow is everything out of A minus everything into A. Okay. And then we have that for everything going out of A, right? Their flow is at least C the capacity minus delta, right? And for everything going into A, their flow is at most delta. Okay, so then we can just combine everything. You can do some math over here. So this, so this is equal to, everything out of A minus this thing over here. Okay, now this thing over here is just like all of the edges which either go into A or out of A. Okay, so at most there are M of these edges. Okay, and whereas this thing here is equal to the capacity. Right, that's the definition of the capacity is how the sum of all the capacities out of A. That's the capacity of this cut A. Okay. Right, so therefore you have that this flow here is at least as large as the capacity minus m delta, which implies that the max flow is at most, the current flow plus m delta. So somebody's asking, what does m stand for? M is the number of edges, the total number of edges. Sorry. Okay, any questions? Okay, yeah. So W. What are you asking? Yeah. So altogether, I guess you're gonna type out the full question because I'm not sure what you're asking. But anyways, so let me just summarize everything. So what we did was we found this capacity scaling algorithm, right? Sorry about the mess. And we showed that this algorithm terminates in this amount of time. Okay. Yeah, so this algorithm is basically like Ford-Fulkerson, except for we remove all of these small edges in the beginning. Okay, what does m times n times c mean? Okay, so m is the number of edges, n is the number of nodes, and c is the maximum capacity. Okay, yeah, right. So here we're saying like the running time here is going to be number of edges squared times log of the max capacity for this thing. Okay. All right. So now I'm going to switch over to what should be today's lecture. Okay. So by the way, I'm sorry that I forgot to upload these notes to Blackboard last night. Okay. So if you don't have them, so they're currently on Blackboard. Okay. So just get them from Blackboard right now. Right. So what we're going to talk about now are some applications of max flow, okay? Because it turns out that these two problems, max flow and min cut, okay? So they're different problems, first of all, okay? But it turns out that many problems are related to either max flow or min cut, okay? So therefore, if you can translate those other problems to a max flow problem or min cut problem, you can solve those other problems. Okay, so here's just like a list of some problems which are can be sort of transformed to either max flow or min cut. Okay, so there's like a big list of these problems. So this is why I say that these two problems, max flow and min cut, they're really, really important problems in combinatorial optimization because you can transform many other problems to these problems. All right, so unfortunately, I'm not going to have time to go. So there's a lot of stuff to cover in this chapter, okay? And I'm not going to have time to go through all of them. I'm going to pick out a few important things, okay? So hopefully these things show you. So what I'm going to do is show you how to transform certain problems into max flow or min cut problems, okay? So hopefully by showing you a few examples, you get the general idea. And then you can go through parts of this chapter which I will not cover today, right? You can just look at it by yourself to see how to do some of these other transformations. Okay, so they're quite interesting, so I do recommend that you look at them. Okay. Now, for the things I do not cover, then I also will not include them on things like exams or homeworks. Okay, so I'm basically gonna just only include things in the exams which I do cover today. Okay. But still, whatever I don't cover, you should still look at because they're interesting materials. Okay. Lecture 9. Okay, so guys, are you seeing? So what you should be seeing right now is something that says applications of max flow. Is that what you're seeing? It seems the screen is stuck. Oh, okay. All right. So I think there's something wrong with. Let me modify this this sharing thing. Okay. Let me just share everything. Okay. So, okay. Now, guys, do you see? So I just wrote the word hi. Do you see that? Okay. You see it now. Okay. Okay. All right. Fine. Okay, sorry about that. Yeah, so what I was saying was, you have max cut and max flow and min cut. There's also, yeah, and these are related to many other problems, but I'm not going to cover all of them today, okay? Yeah, so one thing I'll cover is bipartite matching, okay? So first of all, what is bipartite matching? Well, let's look at the general matching problem, okay? So you're given a undirected graph G, okay? And a matching is basically, we find a subset of the edges, Okay, for example, these blue edges in this graph. Okay, and the requirement is that the edges cannot touch each other. Okay, so for example, you see that none of these edges touch each other. Okay, now if I add this other edge over here, then this would touch one of the existing edges. Okay, so this is not allowed in a matching. So another way to say this is that for each node, okay, right? So this node is part of several edges, but in a matching, this node can be at most one of the matched edges. Okay, you cannot pick, for example, this edge and this edge, because then this node would be part of two different matched edges. Okay, so in a matching, each node is only part of one matched edge at most. Okay, so this is a matching, and there are various there are a number of applications for this. Okay, now we're going to look at bipartite matching. So bipartite matching, first of all, we're going to restrict the graph to be a bipartite graph. Okay, so bipartite graph just means that you can take all of the vertices, right, and you can divide them into two parts, the left part and the right part. Okay, right, like over here, the left and the right parts, and the edges only go between the left and the right edges. The left and right vertices. Okay, like here you don't have any edges between left vertices. Okay, and you don't have any edges between right vertices. You can only have edges between the two sides. So that's a bipartite graph. Okay, and bipartite matching just means that you want to find a matching in this bipartite graph. Okay, so for example, here you have a matching with 3 edges. Okay. Right, and for maximum matching, okay, so sometimes you want to find as many edges as possible to match. So this just means that you want to find as many edges as possible which do not touch each other. Okay, so in this graph, you can find 4 edges which do not touch each other. Okay, right. So the problem we're trying to solve is this maximum matching. Okay, we're trying to find the maximum number of edges which form a matching in a bipartite graph. Okay, so it turns out that you can solve this problem using MaxFlow, okay? Because you can take one of these bipartite graphs and you can transform it to another graph, and then you can run MaxFlow on this new graph. Okay, so we're going to form this new graph G prime. Okay, so this is going to be our G over here, and you're going to form a new graph G prime, and G prime is actually almost the same as G. Okay, the only difference is that we're going to add 2 nodes, okay, S and T, right? Because in the original graph, you don't it's a bipartite graph, so you don't have any other nodes, okay? But in our G prime, we're going to add S and T, and furthermore, you're going to connect S to every single node on the left, okay? And you're going to connect T to every single node on the right. Okay, so you have edges which go from S to every left node, and then you have edges which go from the right to T for every right node. Okay, right. And because you want to make this into a into a MaxFlow problem, you also need to set capacities on these edges. Okay, so therefore, for all of these new edges that we add, we're going to set their capacities to 1. Okay, all of them. Okay. And for the old edges, right, because originally this was our G, right? This was our original G. And so these edges, we're going to set their capacities to be infinite for all of these edges. Okay, so infinite just means that there's no restriction on how much flow you can put through these edges. Okay, so that's how you form G prime. And now now we have this claim, okay, which is that if you're trying to find the maximum size matching in G, the original graph, okay, then this is going to be equal to the value of a maximum flow in the new graph G prime. Okay, so therefore, since we know how to find a max flow in G prime, then we can use that to find a max matching in G. Okay, so how do we prove this? Well, we're going to prove, these two things are less than or equal to each other, and then also greater than or equal to each other. Okay, we'll prove both directions. Okay, so first of all, we're going to prove that the maximum matching is at most the size of the maximum flow. Okay, and the way we're going to do that is you're going to start with a matching over here. Okay, and you're going to transform it into a flow. And so this is going to be the max matching. Okay, so M star here is going to be the maximum matching, and you're going to transform it into some sort of flow. And so this flow is at most the maximum flow, right? It's less than or equal to the maximum flow. Okay, so therefore you can take what we did was you take a maximum matching and then you transform it into some flow, and this flow is less than or equal to the max flow, and so that lets you prove this this less than or equal to direction. Okay, right, now the way we're gonna transform this matching to a flow is that sorry, let me just erase this stuff. Okay, is that for all of these nodes on the left and the right that you use, right, we're just gonna, so in the flow, we're just gonna take the source and connect them to all of these nodes, okay, right? And then for all the nodes on the right, we're gonna connect them to the sink, okay? Now, for example, this node, this 3', right, this is not used in the matching, right? This 3' is not used in the matching, so therefore it's not connected to T, okay? And this 5 here is not used in the matching, so it's not connected to S. Right. So anyways, so now we took this matching and you made this new thing out of it, and we claim this new thing is actually a flow. Okay, it's a valid flow. Because what you can do is you can just put a capacity of 1. You can put 1 unit of flow on this on each of these edges from S to the left, and then you can put 1 unit of flow for all of these right edges to T. Right. And so and so now we satisfy all the capacity constraints. Right? And also you satisfy all the conservation constraints because since it's a matching, then for each node, it's only connected to one other node on the right. Okay, so therefore it's got 1 unit of flow going in, and because it's only connected to one other node on the right, it also only has 1 unit of flow going out. Okay, so therefore you have you satisfy the conservation constraints at all of these nodes and the capacity constraints. So therefore this whole thing is a flow, is a valid flow. And this thing is at most less than or equal to the maximum flow. Okay, so that's one direction of the proof. Okay. Now the next direction of the proof, we want to show that the max flow the matching is at least the max flow. Okay, so so now what we're going to do is we're going to start with a flow, right? G prime here is a this thing on the left is a flow, and then you're going to transform it into a matching. Okay, so this is just some sort of matching over here, right? And so this matching can be no more than the optimum matching. Okay, right. So now suppose you have so this here is going to be the max flow. Okay, and the max flow will be transformed into some sort of matching, which is no more than the max matching. Okay, so the way we're going to do this transformation is you're going to take the flow, and then you're just going to like cut out all of these extra edges. Okay, because these edges are not part of the original graph. Right? Is there some question? So somebody's said something. Right. Okay. So, anyways, we're gonna take out all of these edges from S to all these other nodes, and also the edges that involve T. Okay. And we claim that whatever you have left over, okay, we claim that this is a matching. Okay. So why is this a matching? Well, first of all, we know by this integrality theorem, right? Remember that this said that any kind of flow. So if you have integer capacity values, then the integrality theorem says that there is a flow with only integer values in the end. Okay, and if we run like Ford-Fulkerson or capacity scaling, we can find an integer flow. Okay, right. So the reason this is important is because then what we know is that on all of these edges between the left and the right, we know that the flow here is going to be exactly equal to 1. Right. Sorry, I wrote this in the wrong place. Okay. Because each of these nodes has an incoming flow of 1, right? And so, so this node, for example, cannot be connected to several other nodes. Because if it's connected to several other nodes in the flow, right, then, for example, you could maybe send a flow of like 1/2 here on one edge and 1/2 on the other edge. Okay, if it's connected to multiple other nodes, you would have to send like some fractional amount of flow on each edge. Okay, but we know that this is an integer flow, so so each of these nodes on the left sends an integer amount of flow to the right, and so that means that it can only be connected to one other node on the right. Okay, every node on the left which receives some flow is connected to one other node on the right. Okay, so this means that if you have like k nodes in your flow, right, then you also have k nodes on the right which are connected to these k left nodes. And so that means that you have a matching of size k. Okay, so if your flow is equal to k, then your matching here is also equal to k. Okay. And this k here can be at most the maximum matching. So therefore, the maximum matching is going to be at least the size of this max flow, which is equal to k. Okay. Does that make sense? Any questions? Okay. Right. So that's just like one matching problem, right? Bipartite matching. Okay. There are many other kinds of matching problems, which unfortunately I don't have time to talk about. Okay. But I'll just mention one of them, which is this thing called perfect matching. Okay. So perfect matching is just that every node has to be in the matching. Okay. That's what a perfect matching is. Okay. So for example, here you see that some nodes here are not part of a matching. Sorry. Let's go for, yeah. You see that this node and these two nodes, they're not part of a matching. Okay. So this is not a perfect matching. Okay. So perfect matching basically says that, well, first of all, you have to have the same number of nodes on the left and the right. Okay. Otherwise, it's impossible for every node to be part of a matching. Okay. And also, if you have like, let's say k nodes on the left, your matching has to be size k. Right. So here we don't have a perfect matching because you have 5 nodes on the left and on the right, but you only matched 4 nodes. Okay. So that's not a perfect matching. Okay, yeah, so this perfect matching, these problems have been studied for a long time, okay? And basically, people wanted to know, when do you have a perfect matching? Okay, when is it possible? So if you give me a graph, okay, does the graph have a perfect matching or not, right? And, you know, are there any ways that I can tell whether it has a perfect matching? Okay. So it turns out that there's this way of characterizing. So it's like a necessary and sufficient condition for a graph to have a perfect matching. Okay, and this is usually called the marriage theorem because you can sort of think of these left things as like women and these are like men, and you know if you match them, it's kind of like you marry them. Okay, right. But anyways, this problem has been studied for a long time, right, over 100 years. And the condition is actually pretty simple. Okay, so and it's also a natural condition. So what it's saying is that suppose you take a subset of nodes. Okay, any subset of nodes on the left. Let's call this S. And then you look at who are they connected to on the right. Okay, so for example, here, these two nodes are connected to these nodes on the right. So this is going to be neighbors of S. N of S is neighbors of S. Okay. And you see that the size of S is at most the size of its neighbor set, right? Okay, so in fact, if you if you took some other S over here, right, you see that in this graph, like if you took this set of as your S, then the neighbors are going to be what? 1 prime, I guess the neighbors are everybody? Yeah, okay, all right, yeah. Okay, so again, you see that S is at most, the size of S is no more than the size of its neighbor set. Okay. Now, this marriage theorem says that if for every single S on the left, okay, if for every single subset, you have that the neighbors of the set is like, has more nodes than the set itself, then you have a perfect matching. Okay, and this is an if and only if condition. Okay, yeah, right. So so I'm not going to prove this. It takes like a bit of time to prove this, and it's not really directly relevant to what we're doing. Okay, but anyways, I just wanted to tell you about that. And there are many other kinds of matching problems. So for example, we talked about bipartite matching. Okay, now we saw like a bunch of, or we saw, well, 2 algorithms, okay, for max flow. So which one should you use? Okay, if you use the basic Ford-Fulkerson, then the time complexity is m times c, okay, where c is the maximum capacity. Okay, and in this case, Yeah, so it turns out that you don't have to set these, so, we set these capacities to be like infinite over here, okay? But actually, it's enough just to set them to be, to be n, okay, the number of nodes. Okay, so you don't have to set the capacities to be infinite. Even if you set it to n, the algorithm, the theorem still works. Okay, so therefore you can run the generic Ford-Fulkerson in m times n time. Okay. Now on the other hand, the capacity scaling, okay, that takes m squared times log c time, right? And oh, sorry, I think there should be like yeah, well, anyways, the point is that this capacity scaling is actually slower than the basic Ford-Fulkerson in this case, because the maximum capacity in this graph that we build is going to be small, okay? So, so the generic Ford-Fulkerson is only bad if the maximum capacity is large, right? But in this case, our graph is going to have small maximum capacity. So in that case, you actually want to run Ford-Fulkerson instead of capacity scaling. Okay. But there are other even faster algorithms. For example, this shortest augmenting path and many other algorithms can be even faster than the generic Ford-Fulkerson. Okay. All right. Now, something else to say is that you can also look at matchings in non-bipartite graphs, right? So, for example, we started with a non-bipartite graph, and you can also try to find maximum matchings in these. Okay. Now, these are going to are more complicated. But there's like this well-known algorithm called this Blossom algorithm, okay, which takes n to the fourth amount of time. N is the number of nodes. Okay. But there's a much faster algorithm by Macaulay and Vazirani, which takes it's basically the same amount of time as to solve bipartite matching. You can also solve non-bipartite matching. Okay. Right. So we're not going to talk about those algorithms. Those sometimes are not even based on flow algorithms. Okay. But I just want to mention that matchings are like a very rich field of study, and there's many other algorithms for these. Okay, so now something else I'll talk about is the disjoint path problem. Okay, so disjoint path is you're given a graph with two special nodes S and T, and you want to find paths from S to T in such a way that the paths do not use the same edge. Okay, so for example, you see the blue path and the purple path, right? They use different edges. Okay, and this is useful because if you think of this graph as like a communication network, right? Then if you're sending data on one path, or if you're sending data on two different paths, you don't want the paths to overlap because then you'll get a bottleneck, right? So for example, this path and the other path overlapped, you'll get a bottleneck on some of these edges because there are many paths using the same edge, and you would get a bottleneck. Okay. So if you don't want these bottlenecks, then you want to find disjoint paths. Okay. And since you want to send as much data as possible, then you want to find as many disjoint paths as possible. Right? So in this case, we found 2 disjoint paths. Okay. Can we find 3 disjoint paths in this graph? Well, no, we can't. Okay. So the maximum number of edge disjoint paths is 2. Okay. Now, I should mention that this is edge disjoint, meaning that the paths cannot use the same edges, but they can reuse the same nodes. Okay, you see, for example, here these 2 paths both use node 3. That's okay. Right? You could also look for things like node disjoint paths or some combination of that. Okay, but right now we're just going to look for edge disjoint paths. Okay, so yeah, so we want to find as many edge disjoint paths as possible. So again, we're going to translate this to a flow problem, a max flow problem. Okay, because this problem kind of looks like a flow problem, right? Because you're trying to send stuff from S to T. Okay, both in this problem and in max flow, you're trying to send as much stuff as possible. So it kind of you see that connection there. Okay. So in fact, the theorem is that the maximum number of edge disjoint paths, okay, is equal to the max flow value. Okay, so that's what we're going to prove. Okay, so again, we're going to prove 2 directions. We're going to prove the left or less than or equal to direction first. Okay, so so this means that if you have a bunch of edge disjoint paths, then we have to show this is no more than the max flow value. Okay, and the reason this is true is because suppose you have let's say a path like that and a path like that, and maybe some other some other path like this, okay, right? Okay, so now each of these paths, so we're going to build this graph where this flow graph where all of the edges have capacity 1. Okay, and now for each of these paths, right? We're going to send 1 unit of flow on each path. Okay, so you send 1 unit of flow on this path, you send 1 unit of flow on this path, and you send 1 unit of flow on this path. Okay. All right, and now we claim that so we have P of these paths, right? We have P1, P2, and P3. Okay, and the claim is that now if you put all of the flows together, okay, so we have 3 different flows here, right? Each of size 1. If you put all the flows together, you get a valid flow of size 3. Okay. Now, the reason you get a valid flow is because these paths are edge disjoint. Okay. Now, if these paths are not edge disjoint, okay, so for example, let's say this path goes like this and this path goes like that. Okay. Then if you try to send a flow of 1, then if there are these edges which they both use, you would need to send a flow of 2 on these edges. Okay. But that's not a valid flow because in our graph, all the edges have capacity 1. Okay, so if the paths are not edge disjoint, then you cannot put them together into a valid flow. But because they are edge disjoint, then for each edge in this in all of the paths, we are only going to send 1 unit of flow, at most 1 unit of flow. Okay, and so therefore we can satisfy all of these capacity constraints, and we get a valid flow. Okay, and so that valid flow can be no more than the max flow. Okay, all right, so that's one direction. The other direction is that now we're gonna suppose that you have a max flow value of k. All right, so in this graph, for example, let's say that you found some sort of max flow. Okay, so let's see, so maybe well, all right, so the idea basically is that if you find a max flow, okay, so this flow is going to look maybe something like that, right? Okay, so what you can do with this max flow is you can use it to find a bunch of edge disjoint paths. Okay, so how do you use it to find these edge disjoint paths? Well, the flow goes from S to T. Okay, so let's just sort of do like let's say a BFS or something in this flow graph. Okay, so the flow graph is going to use some edges in the graph and not use some other edges. Okay, so how would I draw that? Let me, it's kind of hard to change colors here. How do I change? All right. Okay, all right. Yeah, so let's say that, there are these other edges which are sort of not being used. Okay, sorry, this is a bad drawing. But anyways, so there are some edges in the graph which are these red edges which are used in the flow. And there's some additional edges which are not used in the flow, okay? So what we're gonna do is we're just gonna only look at the edges which are used, and then you're gonna try to find a path from S to T, okay? Now, it's guaranteed that there is a path from S to T, okay? Because you managed to send k units of flow. So the flow has to get from S to T in some way, okay? There has to be some path by which you can get from S to T. So we're just going to find one of those paths, okay? Right? And then, so we know that on this path, because the capacities in the graph are all 1, right? Then after you find this path, you're going to basically remove all of these edges, okay? So this is a path from S to T, and we basically used this path, okay? Because, right? And now you're going to remove all of these edges, and now your flow is going to have a value of k minus 1. Because previously, let's say you sent 2 units of flow from S to T, and now after you take out this path, which contains 1 unit of flow, then the remaining edges in this flow is like a flow of size 1. Okay. Now, in this remaining graph, we're again going to find a path from S to T. And again, it's guaranteed that you can go from S to T because, we managed to send 1 unit of flow from S to T, so there has to be some path that goes from S to T. Okay, so then now you can find this other path, right? And now once you find this other path, you're also going to take it out. Okay, and let's say that there was let's say that in total you sent 3 units. Okay, so after you take out this thing, right, then now your flow has size 1. And again, you can find a path from S to T of size, you can find another path, okay? Right. So now the point is that each of these paths you find is edge disjoint, right? Because each time you find a path, you just take out all the edges. Okay, so every new path is disjoint from all the previous paths. Okay. And because you had a total flow of k, then you can take out these paths k times, and so therefore you can find k number of disjoint paths. Okay, so this means that the maximum number of disjoint paths has to be at least larger than this is right. Anyways, if this is k over here, right, then the maximum number of edge disjoint paths has to be at least k. Okay, any questions about this? Okay, so all right, so so this edge disjoint path problem, okay, this is related to some other problem which is called network connectivity. Okay, so it's basically suppose you have S and T and you want to make sure they can communicate. Okay, now sometimes if you remove some edges, then you can make sure that S can no longer communicate to T. Okay, so for example, if you remove these two edges, you see that now there is no path from S to T. Okay, you've disconnected S and T. And so now your question might be like, what is the minimum number of edges I can remove to disconnect S and T? This is kind of like how robust is my network, right? Because if my network, if I just take out one edge and I disconnect like S and T, then my network is not very robust, right? It's very, if even one thing fails, my network is disconnected. That's bad, right? But if like I have to remove like 100 edges to disconnect S and T, then my network is very robust. Yeah. So so there's this famous theorem by Menger, again almost 100 years ago, which says that it relates the number of edges needed, the minimum number of edges needed to disconnect your network. Okay, that is equal to the maximum number of edge disjoint paths. Okay, so so what we're saying is you can look at these two pictures. Okay, you can see that these two so you have two edge disjoint paths, right? And you can see that if you take out one edge from each path, then you've disconnected S and T. Okay, yeah. So so it's saying that so this is the theorem. Okay. Right now, I'm not gonna. I don't have time to prove this, unfortunately. Okay, it's actually not hard to prove. You can just you can take a look at the notes, and I think you get the basic idea. Okay, yeah. All right. So one thing I want to talk about is another problem, which is called circulation. Okay, so circulation is very similar to max flow, except for in the circulation problem, you don't have the special source node and the sink node. Okay, you don't have these. Okay, what you have is just a graph like this where you don't have anything which is special. Okay, there are no special nodes in here. Okay, I shouldn't draw these things anymore. Yeah, so instead, what you have is that every node can potentially be a source or a sink. Okay, so what I mean by that is you see these green numbers on top of the nodes. Okay, so if you have a negative number, then what's happening is that this node wants to get some flow. Okay, and what it wants is that, if you take all the flow coming into this node and you subtract all the flow going out from this node, then you want this to be equal to -8. Okay, so so this node is actually generating flow. Okay, so if you think about like these nodes with like positive values, they want to take in additional flow. Okay, these are like sinks. Okay, and then these nodes with negative values, they're like sources. Okay, they produce flow. Like maybe this node here with a 10, it's like sort of consuming oil. Okay, right, and then this node with a -8, it's like a country that produces oil. Okay, so you can think of it that way. Okay, and otherwise, it's similar to the max flow problem in that you have these edges which connect nodes, and then they have these capacities. Okay, and you can send flow on these edges, but you cannot exceed the capacities. Okay, now the main difference is that you don't have this conservation constraint in the max flow. Okay, in the max flow, every node except for the source and sink, you have to, if you take the inflow minus the outflow, this is equal to 0. Okay, in circulations, if you take all the inflows minus the outflows, it has to equal these special values that you're given. Okay, so these green values are part of your input now. Okay, so the so the circulation problem is that if I give you these demands or supply values, okay, then does there exist a flow which can satisfy all of these D values? Okay, because it could be that I give you a bunch of D values and it's just not possible to find any flow which satisfies all of them. Okay, so for example, if all of the nodes demand like positive, if all the nodes are sinks, right? If they all want to get more than they receive, okay, then that's not possible, right? Because where's this going to come from, right? Like if all countries want to consume oil, but no country produces oil, right? This is not possible to satisfy. Okay, yeah. So so there are some conditions where it is possible to get a circulation, and there are other conditions where it is not possible to get a circulation. Okay. Right. Now, so let's look at some of these conditions. I think I won't have time to prove these conditions. Okay. So so the basically so to solve this problem, you can first of all, if you add up all of so the condition for when is it possible to have a circulation is that if you add up all of the demands, okay, all these green values, okay, so you can go add them up and you'll see that they add up to 0. Okay, and this is a necessary condition in order for there to be a circulation, is that all of these demands have to add up to 0. Okay, yeah. In other words, if you look at all the positive demands, right, this has to be equal to all of the negative demands. And this is kind of natural because, again, if you think about like, whether I want to consume oil versus produce oil, okay? If like you have, if I want to consume a total of like 1 million barrels of oil, right, then there has to be some nodes which produce a total of 1 million barrels of oil, right? Yeah, so the total consumption and the total production have to match each other. Okay? This is a necessary condition. Okay, now, however, what if you actually want to find a circulation, right? Then the way that we can do this is, again, you can use a max flow formulation. Okay. So the way that we're going to do this is you're going to start with a graph on which, so we're trying to find a circulation in this graph, okay? And we're going to convert this to a max flow. And to do this, you just add a source node and a sink node, right? I mean, these are not part of the circulation, but we're going to add them in. And furthermore, for the capacities of the source and sink nodes, right, we're going to make them, so for each node, okay, if this node has a negative negative value, okay, negative D value, okay, meaning it wants to get extra, or sorry, it produces extra flow, okay. So in that case, we're going to connect it to S. Okay, so if your value is negative, you connect it to S, okay. If your value is positive, for example, this guy, right, you connect it to T. Okay, so T is connected to all the positive values, S is connected to all the negative values, and also the capacities of these edges, okay, is exactly equal to the D value. So for example, S here is connected to this guy, right, and his D value is -8. So you set the capacity to +8. Okay, likewise, this guy is connected to T, right? And his D value is 10, right? And you set the capacity to T to be 10. Okay? Right. And then, and then there's a claim that this original graph G has a circulation if and only if this new graph has a max flow value of D, okay? Where D is simply defined as the sum of all of the positive demands or the sum of all of the negative demands, right? We know that these two things have to be equal to each other. And so whatever value that is, right? If you can find a max flow of value D, then this graph has a circulation. Okay, so that's how you can tell whether a graph has a circulation or not. Okay, so I'm not going to prove this theorem for you. Okay, yeah. So if you want to see the proof, you can go look in the algorithm design book, right? The Kleinberg book. Okay, yeah, right. So right. So one thing I'll mention is that why are circulations useful? Well, I mean they're useful in their own right. Okay, but they're also useful because you can create another problem, which is circulations with demands and lower bounds. Okay. So for the lower bounds, what we're saying is that for each edge, okay, not only do you have a maximum capacity, so your flow cannot exceed 9, okay, you also have a lower bound so that your flow has to be at least, let's say 2 or some other value. Okay, so now we have a new problem where we have both these demands and upper and lower bounds on each edge. Okay, and it turns out that this problem, even though you add lower bounds, okay, it's very easy to transform this problem into the original circulation problem without lower bounds, right? So this one doesn't have any lower bounds, and if you do have lower bounds, you can just transform it to the circulation without lower bounds. Okay, but so therefore you can solve this problem efficiently. Okay. Now, if you can solve this problem, then there are many other problems where you have where naturally you have some sort of lower bound. Okay, you don't just say that I can't send too much stuff. You also say that I need to send at least some amount of stuff, right? Like for example, if you're running like some company, some like what is that, Shunfeng company, okay, right? You can't send more than, let's say, 1 million packages a day, but you also want to send at least, let's say, 500,000 packages a day, okay, right? So you have these natural upper and lower bounds, and in this case, we can solve it using these circulations with demands and lower bounds. Okay, yeah, so sorry, I'm going to skip over exactly how you do this. So this survey design problem, okay, you can look at this. It's actually pretty straightforward, okay? And this problem has upper and lower bounds, and so you can use it to, right, so this has upper and lower bounds, so you can use it to, you can use the circulation with lower bounds to solve this, okay? All right, now one last application. Okay, so I'm going to go over time by a few minutes, but this is kind of an interesting application, which is that you can actually use, so far we talked about using max flow to solve certain problems, right? But you can also reduce some problems to min cut. Okay, so even though max flow and min cut, their values are equal to each other, but they're different problems, right? I mean, they're very different problems. Okay, so sometimes it's easier to change your problem to either max flow or to min cut. Okay, now in this case, we're going to look at this image segmentation problem, and it's more natural to change it to a cut type problem. Okay, right. So the problem that we're going to look at is so we have this image segmentation problem, which is that if I give you like a picture like this, okay, so there you can think of it as like a foreground and a background. Okay, so I mean, these are not like very well-defined terms, but basically foreground is like stuff close to you, and background is like stuff far away from you. Okay, so for example, these two firemen are close to you, and the wall is like far away. Okay, so now you just want to segment this image, meaning that you want to pick out all of the foreground stuff, the stuff close to you, right? And you want to leave all the background stuff. Okay, so for example, if you segment, right, then you have this mask for these two firefighters. Okay. Right. So this image segmentation problem, I mean, this is like a people care about this in things like computer vision, and nowadays you would use like machine learning to solve this problem, right? But before all of these new machine learning methods, people had other methods for solving these problems. Okay. So let's see. Yeah. So let me introduce the background for this, and then I'll finish this in like 5 minutes next time. Okay. But let me just give me 2 minutes to introduce how we can phrase this problem as sort of a graph problem. Okay. So what we're going to do is you're going to take your image and then treat it as a grid of pixels. Okay. And now all you need to do is for each pixel, you need to say whether it's in the foreground or in the background. Right. For every single pixel, you make a choice whether it's in the foreground or the background. Okay, so now let's let V be the set of pixels. Okay, so V, we're going to think of this as a graph, right? Where these are all of the nodes in the graph, right? And then these are all of the edges, right? And we're only going to make edges between neighboring pixels. Okay? Right, now for each pixel, okay, let's say that you have some sort of probability. Somehow you can compute a probability that it's in the foreground. Okay, so for example, maybe the foreground pixels are like brighter or something like that. Okay, but somehow you compute a probability that it's in the foreground. Okay, and you compute another probability that it's in the background. Okay, maybe it's like dark or something. Okay, okay, and one final thing is that, okay, is that because your images are like continuous, right? Then usually if one pixel is in the foreground, then its neighbor is usually also in the foreground. Right? I mean, that's not always true because you could have a pixel on the boundary and its neighbor is not in the foreground. Right? So you can switch from foreground to background once in a while. But because your images are pretty continuous, you don't want things like where it's foreground, background, foreground, foreground, background, foreground, background, over and over, right? You don't want to produce some sort of very noisy segmentation like that. Okay, so therefore you have this penalty, which basically says that if this is selected to be the foreground, right, then if I select this neighbor to be in the background, I have to pay a penalty. Okay. Right, so therefore, now we can phrase our segmentation problem in the following way. Okay, we are trying to find we're trying to take this graph and you're trying to partition it into two parts, A and B. Okay, so A is some subset of the pixels, right? Some subset of the pixels. B is this black part, right? Yeah, so A is a foreground, B is a background. And what you want to do is you want to maximize the probability that all of these foreground pixels, right? Each of them has this probability they're in the foreground. So you want to maximize the sum of their probabilities, right? And then for these background pixels, each of them has a probability they're in the background. So you also want to maximize that probability, the sum of those probabilities. Okay. And finally, you do not want to separate neighbors. Okay, so if this guy is in A, which is a foreground, right, you don't want the other neighbor to be in B. Okay. So therefore, for each edge, okay, if you have that A, if you have A intersect this edge, this condition, this basically means that this was chosen to be in the foreground and this was chosen to be in the background. Okay, when that happens, you need to subtract a penalty like this. Okay, so that's the problem. So we're trying to maximize this quantity, which basically expresses how likely are these pixels to be in the foreground or background minus the separation penalty. Okay, all right. So next time we're going to see how to solve this problem using a min-cut formulation. Okay, all right. Yeah. So any questions about anything? All right, so then then I'll continue next Tuesday. Okay, so we're again going to be online next Tuesday. Okay, so then talk to you guys next Tuesday. Okay, so yeah, the class is over, but if you have any questions, you're welcome to ask. Okay. Does anyone have any questions? You can just type it out or you can say it. Lecture 9, page 52. Okay, 1 second. Oops. All right, page 52. Okay, yep. Why B to A FE is less than delta? Oh, okay. So you're asking about this? Okay. Yeah. The reason is if this flow here is larger than delta, right? Then remember how you make these residual graphs, which is that anytime you can send flow, then you're gonna add this reverse edge, right? So if the flow here is larger than delta, you're gonna add this reverse edge, and the capacity of this reverse edge is like larger than delta. Okay, if it's larger than delta, then it will be included in this GF delta graph. Okay, but if it's included in this GF delta graph, right? So if you actually have this edge, then B would be reachable from S, and so this node would actually this node would be reachable from S. So you would actually include it in A and not B. Okay, so that means that this edge here cannot be cannot be more than delta.